Creating beautiful things with code can be easy if you take it step by step. Everything makes sense if you break it into individual parts. Let me show you how to take basic programming principles, functions, arrays, and for loops to create complex animated code bases. Once we fully understand the techniques, we will take it to the next level in the advanced section. Today, we will discover the tools, we will experiment with code, and we will use that knowledge to design our own animations. Let's make art with code and learn programming at the same time. Have fun! Don't forget to click the like if you want more tutorials exploring different creative coding techniques. Flow field is a grid of angles. We can also call it a vector field. If we add particle system on top of it and make the particles flow over the grid, their motion is influenced by the field. Vector, the direction and speed of movement, will be influenced by the angle value stored in the cell each particle is currently moving over. This class is for creative people who want to understand how the code works under the hood. Today, I want us to understand how things work and gain full control over the effect. We will be able to do anything we want with it. Knowledge is power. That's why I will use vanilla JavaScript with no frameworks and no libraries, as usual, just the basic coding techniques. If you are a beginner, I made a warm-up class where we cover these techniques at a slower pace. Check out the full extended version where we go from basics to advanced step by step while building multiple projects. Links in the description down below. Hope you get a lot of value today. This class is beginner friendly. Basic knowledge of HTML, CSS and JavaScript is required to get the maximum value. I created a very simple web page in index.html and I positioned my canvas element with CSS. Everything else in this project will be handled by JavaScript here in script.js file. As always, I need to set up my canvas. Custom variable called canvas will be document.getElementById and ID I gave it was canvas1. CTX context is that canvas variable dot get context and I pass it 2D to create an instance of canvas rendering context object. Now, this CTX contains all built-in 2D drawing methods and properties that any web browser can understand. I want to have a full screen effect today, so width will be window inner width and canvas height is window inner height. I'm not sure if you can see it, but doing this gave my web page scroll bars. I don't want them, so easy fix is to give canvas element position absolute. Like this. Nice. So this entire black area is our canvas, our drawing board. I can use CTX variable from line 2 to draw something now. If I console log it, we can see the default canvas settings. For example, I can see that the default canvas fill style is black. To make sure the shapes we draw are visible against the black background, I set fill style to white. Down here, we can see all built-in canvas drawing methods. For example, the arc method, which can be used to create an arc or a full circle. If we had more shapes on canvas, I would have to call begin path, but now I can skip it and let's say I want a circle with a center point at coordinates 100 horizontally from the left edge of canvas and 100 vertically from the top edge. Radius of the circle will be 50 pixels. Start angle of the arc will be 0 radians, and since I want to draw a full circle, the end angle will be math.pi times 2, which is approximately 6.28 radians or 360 degrees, full circle. Arc method works with a path, so it doesn't directly render anything on canvas, it just positions an invisible path. We can choose to stroke that path or to fill that shape with color. So I call built-in fill method like this. I can move the center point of the circle around. I can change the radius. I can even change the end angle or start angle to get a different shape. Okay, so our canvas is set up and we tested it by drawing a shape. In this area, I will keep my global canvas settings to keep our code organized. Today, we are building animated flow field. It will be made out of individual lines. So how do we draw a simple line on canvas? We start by calling built-in begin path method. This will start a new path as well as close all previous paths if there are any. We call move_to method to set starting x and y coordinates of the line. We call a line_to method to set the ending coordinates, or we can chain multiple line_to to create a more complex shape, which is what we will be doing today. Same as the arc method, move_to and line_to methods just set a path. They don't directly render anything on canvas. Now we have to choose if we want to stroke the path or if we want to fill that shape with color. I will call built-in stroke method to draw the path. Default stroke style is black, so it's not visible against the black background. I go up here and I set stroke style to white. Now we can see we are drawing a line from coordinates 100, 200 to coordinates 400, 500. By default, the line is 1 pixel wide. I can use line width property to set it to 10 pixels, or 100. I can also use line cap and set it to round, for example. Okay, so this is how we draw and style lines on HTML canvas. This is all we need to know to create a wide variety of effects. I want to create many animated lines that will flow around our canvas. So I will use a JavaScript class called particle, like this. Each particle will be moving around and we will connect its positions with a line. JavaScript classes are blueprints to create many similar objects, and we are about to build a so-called particle system made out of many particles. I will also have a class called effect. This could have been just a simple object because we will only have one instance of this class. It will be the main brain of our codebase. So we have particle class, a blueprint we will use whenever we need to create a new particle object, and we will have effect class that will manage the entire effect, all the particles at once. I'm using classes and object-oriented programming to keep our code clean, well organized and easy to read. This is a tutorial for beginners, so I want everything to be clean and as easy to understand as possible. It's my main goal. Effect class will need to be aware of available canvas space, so constructor will expect width and height to come as arguments from the outside when an instance of this class is created using the new keyword. Inside, I convert these arguments into class properties. Take width, passed as an argument here, and convert it to width property on this instance of effect class. Same for height. Effect class will have initialize method. This method will run just once to set everything up. We will have this.particles property. This will be an array that holds all currently active particle objects. So when we initialize this effect, we want to take this.particles array and we want to use built-in array push method to push one new particle into the array. That particle will be created using the class we defined on line 11. So let's write that particle class right now. Every particle will also need to be aware of canvas width and height, because it needs to know when it moves outside the canvas area. To keep our code modular, instead of pulling canvas size from lines 3 and 4, I will take that value from the main effect class. I want to access these properties from lines 19 and 20. I will give particle class access to the entire effect class. Particle class constructor will expect effect as an argument, and inside we convert it into a class property. So here we are pointing towards the main effect object. Keep in mind that objects in JavaScript are so-called reference data types. We are not creating a copy of effect object every time we create a new particle. We are just pointing to that same space in memory that holds the effect class from all the particle objects. That way, particles have access to all methods and properties on the main effect class, and also if any of these properties update, because we are just pointing to that effect object, any changes on the effect object will be immediately visible from the particle objects, which will be very useful for us today. As I said before, we will have one effect object to manage everything, and we will have many particles, hundreds or maybe thousands. Let's see how it goes. Each particle will have starting x and y coordinate. Horizontal x coordinate will be a random value between 0 and this.effect from line 13, .width. We are accessing this property from line 20. Vertical y coordinate will be a random value between 0 and this.effect.height. To avoid sub-pixel values, it's a good practice to use integers, whole numbers without decimal points. By wrapping these in math.floor, this will round the value down to the nearest lower integer. Each particle will have a public draw method. This method will expect context as an argument to specify which canvas we want to draw on. I pass it as an argument, like this, to keep our code more modular and less dependent on the outside environment. Then we take that context and we call built-in fillRectangle method. FillRectangle method is very simple. It will just take these randomized x and y coordinates we just defined and it will draw a rectangle there. Its width and height will be, for example, 10 times 10 pixels. We have our particle class and we have effect class. I want to create an instance of effect class. I create a custom variable, I call, for example, effect, and it will be equal to new effect, like this. The new keyword will look for a class with that name, it finds it up here, and it will trigger its class constructor. On line 23 we can see that effect expects width and height as arguments. So we pass it canvas width from line 3 and canvas height from line 4, like this. Now I can take that effect variable and call init method we defined on line 28. Init method will take particles array and it will push one new particle object into the array. We get an error because here on line 12 you can see particle class constructor expects a reference to the main effect class as an argument. It then uses that reference to access width and height properties of canvas. Since we are creating that particle inside the effect class itself, I pass it this keyword, which in this area refers to the entire effect class. Nice. So after we created an instance of effect class and after we call this init method, I expect that particles array from line 26 contains one particle object. I console log the effect class to check. I can see the effect object, it has width and height properties, and if I open this particles array, I can see there is one particle object inside. I check if all properties have values. If I see undefined or none somewhere, it would indicate a problem. All is good here. Now I need a way to actually draw my effect on canvas. I will give it another method I call, for example, render. Inside, I will cycle over all particle objects inside particles array using array for each method. For now we know there is only one particle object inside. For each particle object inside particles array, I call its associated draw method. We defined that draw method on line 17 and we can see it expects context as an argument, so I take render method and I call it. We need this context, so I take ctx from line 2, I pass it to render. Inside render it will be expected as context and we pass that context reference along to draw method, because we know it's expected on line 17. From there, fillRectangle method is called and our particle is drawn. Nice! I can change the width and height. When I refresh the browser window, x and y coordinates from lines 14 and 15 get randomized and particle is drawn. On the main effect class, I create a property I call number of particles. Initialize method will run just once to set our effect up. Inside, I will create these 50 particles. I can do that by using a for loop. It will run 50 times, and every time it runs, it will take particles array and it will push one new particle with randomized x and y coordinates inside. And this is how you create a simple particle system. If you want, you can save this code as a boilerplate in a different folder, because you can use it for so many different experiments, effects, and generative art pieces. I'm calling init method from here on the first page load. I can also remove this code and I call this.init from inside the effect class constructor, because when we create an instance of a class using the new keyword, constructor will run all the code in the blueprint line by line. We can take advantage of that behavior by putting any code in here that we want to run at the same point when an instance of this class is created. We are building a flow field. I want these particles to move around and leave trails, lines behind them. Let's animate this. Speed x, horizontal speed, will be 1. Particles will move 1 pixel per animation frame in the positive direction on the horizontal x-axis. They will move to the right. Speed y will be 1 pixel per frame as well. Positive direction on the vertical y-axis means down. Since both of these forces will be applied to the particle at the same time, I expect the particles to be moving towards the bottom right corner of canvas. Let's see. Motion will be handled inside update method. This method will define a single step in the animation, and when we call this update method 60 times per second, it will create an illusion of motion. For every animation frame, I want to increase horizontal x position of this particle from line 14 by speed x value from line 16. I also want to increase vertical position by speed y. Here inside render, as we cycle through all particles, we trigger their draw method, and we also call their update method we just wrote. This gets called just once, so there is no motion. I need to call this render method over and over. I want to draw particles, update their positions, draw them again at those updated positions, update them again, draw them again, and so on. Calling this over and over will create animation, an illusion of movement. We need animation loop. I create a custom function I call, for example, animate. From inside, I will call render to draw and update all particles, and then I call built-in request animation frame method. I pass it animate, the name of its parent function. So animate runs, render is called, particles are drawn and updated, and then request animation frame method calls animate again. We have a loop. Request animation frame method was designed for this purpose, and it has special features such as it auto-generates timestamps for us, and it also adjusts itself to screen refresh rate. I have a regular screen, so my animations run at 60 frames per second. If you have a high refresh rate gaming screen, your animations will run faster. You can easily use request animation frame and its auto-generated timestamp to set any animation speed you want. Now everything is ready and I can call animate. I expected all particles to move 1 pixel to the right and 1 pixel down per animation frame. They are leaving trails because we can see old paint, their previous positions. If I want to see only the current animation frame, I need to delete canvas between each frame using clear rectangle method. I want to clear the entire canvas from coordinates 0, 0 to canvas width, canvas height. Nice, we are animating. I change speeds. The relationship between speed x and speed y will define the direction and speed of motion. We can also randomize the speed of each particle. How about a random value between minus 2.5 and plus 2.5? Minus value will move to the left, plus values to the right. On the vertical axis, negative values will move particles up, positive values will move particles down. The ratio between randomized speed x and speed y will determine the final direction of movement, and now particles move in all possible directions. I can make the particles smaller. I actually want to draw lines. I call beginPath method to tell JavaScript I want to start a new path. As the particle moves around canvas, for each animation frame it will update its x and y position, and I will keep track of those positions as simple objects with x and y properties inside the history array. At first, each particle will be assigned a random x and y position somewhere within canvas area, and we use these values as the first object, the first element with an index of 0 inside the history array. The start point of the line will be set by moveTo method. We want to start from x and y coordinates of the first object inside the history array. object with an index of 0. Then we create a for loop. It will run as long as there are any more elements in the history array. For every object, all these objects look like this. For each position object inside history array, we will take x and y coordinates of an object at that index. As the for loop cycles over the array, we pass its x and y coordinates to line2 method. So start point of the line, then we run through all positions inside history array and we connect them with a line. Then we stroke that path to actually draw it on canvas. Now I need to make sure positions are being added to the history array as the particle travels around. Whenever we update particle position, we take this.history array and we push an object like this with these updated x and y values inside. Nice, it looks like it's just one straight line, but it's actually a shape made out of many smaller line segments. I can, for example, make it wiggle by adding a random value between -1.5 and +1.5. This should make it more visually clear that these lines are made out of segments. I can do the same thing vertically. I can increase the random range, maybe from -2.5 to +2.5. I can increase the range even more, a random value between -7.5 and +7.5. Finally, this is starting to look interesting. Right now, these are just endlessly growing lines. What if I want to define max length of a line? In this case, this will mean max number of segments. Inside the update method, I say if the length of a history array is more than max length, call built-in array shift method. So we have two array methods here. Push method adds new element to the end of an array. Shift method removes one element from the beginning. Because we are adding new elements to the end of the array, shift method removes the oldest segment, so our lines crawl around like this. They kinda look like small creatures under a microscope. I could just give them some AI and make this into a game. I can increase max length of the line to 100 segments, or I can do a random value between 10 and 110. Now, some of them have short and some have very long tails. I can also apply trigonometry. Each particle will have angle property, which will initially start at 0. For every animation frame, I will increase angle by some small value. Angle value is in radians. Then I can pass that ever-increasing angle to math.sine, which will automatically map these values along a sine wave. This will give the horizontal coordinate a regular wave motion. Look what happens when I do this for the vertical position as well. Instead of adding here, I try multiplication. I do it for both. Combination of sine and cosine will map the positions along the radius of a circle. Multiplying it by a value like this will increase the radius. You can try to use different combinations of values and apply different operations if you want to experiment. There are many things that can be done here. Basically, we built a particle system where each particle draws a line behind it. I comment out line 69 for a while. Now my goal is to make these lines travel around the canvas following a specific order to create a flow field effect. Flow field is based around a grid of angles. Each cell in the grid stores an angle value, and each cell in this grid in the flow field has a relationship with its neighboring cells. They are not random, they increase or decrease gradually, and as the particle travels over the grid cell by cell, particle's speed and direction of movement is influenced by these angle values, creating a motion pattern. Very common algorithm to generate angle values for a flow field is Perlin noise. It creates a gradient noise that gradually changes values in a random way. The resulting effect looks very natural and can be used to generate textures for procedurally generated terrain or many other things. Today we will generate a spiral flow field where we use sine and cosine values and we attach them to vertical and horizontal coordinate of each point of each cell. This creates a beautiful symmetrical repeating pattern. We will be able to zoom in and zoom out of the pattern for very different end results. Let's take it step by step and it will become clear what I'm talking about as we build it. Our goal now is to create a grid that splits the entire canvas into individual cells. Let's say I want cell size, each cell, to be 20 times 20 pixels. This will split the canvas into rows and columns. The number of rows and columns will depend on the width and height of canvas and on this cell size. I could calculate the number of rows and columns here, but because I want this effect to be responsive, I will calculate that inside init method. We can then call that init method every time resize event happens to correctly recalculate the entire flow field grid. This .flow field will be an array that holds angle values for individual cells in the grid. The number of rows will be the height of canvas area divided by cell size. The number of columns will be width divided by cell size. We will also set flow field to an empty array in case this init method is called while resizing canvas. That way, all the old values will be deleted and we can recalculate the new values. Now I want to travel over that grid. Whenever there is a grid involved, the easiest way to handle it is with two nested for loops. The outer for loop will cycle over the grid row by row from row 0 as long as there are any more rows. The inner for loop will travel over each row from left to right. So we enter the outer loop, we are on the row 0, we enter the inner loop and we cycle through the cells on that row one by one. We reach the end, we exit the inner loop, we enter the outer loop, y increases, and we enter the next row. Again, we cycle through all the positions on that row one by one. We repeat this process row by row until we cover the entire canvas. Each time we enter a new cell, we create an angle value. We can do different things here. I will simply tie x and y coordinate to sine and cosine to create a spiral pattern. We know that if we pass an increasing angle value to sine or cosine, these methods will map these increasing values along a wave. In this case, those increasing values are x and y positions of the cells in the grid, so as we move along the grid, we create spirals and curves. Every time we generate a new angle value, we push it into flow field array. Keep in mind that we are cycling in a grid row by row, generating these values, but we are storing them in an array as a single continuous sequence of values. We need to keep this in mind when we need to extract these angle values again to correctly match them to particles' current x and y position. So at this point, flow field array should be filled with angle values, so let's console log it. I'm actually console logging it after every row. I should have put the console log here after it's all done, but it doesn't matter. We can see that angle values are being generated. Perfect. So we cycled over the canvas in a grid, and for each cell in that grid, we generated angle value, and we stored all these angle values inside flow field array. Because we passed these gradually increasing x and y values to sine and cosine, we created beautiful symmetrical pattern. The pattern will be revealed when we draw the flow field, so let's do it. We already have particles that move over canvas and they drag lines behind them. Currently, we are using this logic to move them. Let's move all this away and completely change this code. In the update method here, I want particles to move around, and the direction of their movement will depend on the position of the particle as it travels over different cells in the flow field. The angle values in the flow field change cell by cell, and this angle will determine the motion of the particle that's currently flowing over that cell. There are many different ways to do this. I will create a helper temporary x variable and it will be equal to particles current exposition divided by cell size. Basically, I'm saying how many cells in our grid from the left edge of canvas this particle currently is, in which column we currently are. Remember that cell size was set to 20. I want integers here, so I will round the value down. Helper y variable will be particles current y position divided by cell size, how many cells from the top we are, on which row. Now I can use these values to map x and y coordinates of a particle to an index in the flow field array. Basically, I have a particle with certain x and y position in a two-dimensional grid. And I have an array which represents that grid, but it's just one long set of numbers. So what I'm trying to do now is to map that x and y position to that index so I can extract the correct angle value from the grid. I know particles' current vertical and horizontal position, and I know over which column and row in the flow field grid it is currently moving. Now I need to use this column and row value to get the angle value of this cell from flow field array. This is a bit complicated to visualize if you are a beginner, so don't worry about it too much. To get index of this position from flow field array, I take the row number we calculated here and I multiply it by the number of columns. That calculates this block. Rows times cells per row, basically. I need to know which cell we are currently in because we added one angle value per cell into flow field array. Then we add however many cells we are into the current row in the grid, like this. This gives us index inside flow field array that holds angle value of the cell we are currently moving over. Then we set angle value of this particle to the index inside flow field array we just calculated. Now we have multiple different options how to use it to achieve different patterns. I will set speed x to cosine of the angle at first. Speed y will be the sine of the same value we just extracted on line 35. Then I take particle's current horizontal position and I increase it by that new speed value. And I do the same for the vertical position, increasing it by vertical speed. I delete this code. So we sliced canvas into an invisible grid. Each cell is 20 times 20 pixels and it has a specific angle value. We calculate which column and which row of this grid the particle is currently moving over. We map that column and row value to index in flow field array to extract angle value that belongs to the cell we need. We increase speed x by cosine of that angle and speed y by sine. This will give us a direction of movement depending on that angle. Then we increase particles' x and y position by these speeds. We push this new particle position inside history array so that we can animate its tail, the line that each particle drags along. If length of the line is more than max length, we remove the oldest segment. I uncomment render to see what motion we get. It doesn't look like it, but we already have a working flow field with sine and cosine spiral pattern. We are just zoomed out really far away from it. It will make more sense as we play with the code now. So the base idea is that passing an ever-increasing angle value to sine and cosine will make the values cycle periodically between -1 and +1. We use x and y positions of each particle as these increasing angle values, so the pattern will be tied to coordinates in that way. I close this in brackets and I multiply it times 2. This will increase the radius of the curve. I remove the rectangle, I only want lines. I make max length of the line to be a random value between 10 and 210 segments. I can use different values here. Let's increase the number of particles so we can better see the pattern. Look what happens if I slowly increase this value. 0.5. I can go much higher than this. I think around 10. Let's put this value into a variable, into a class property I call this.curve. I will show you why I call it curve in a minute, it will be clear. I use that property here. Okay, I can also multiply x and y by a value. If the values are the same, we will get a symmetrical zoom into that pattern. It's not yet fully obvious, but a clear pattern will emerge from this, bear with me. I want these values to be identical for symmetry, and I will put them into a class property I call this.zoom. I set this.zoom to 0.2. Keep in mind that curve zoom is also connected to cell size because of how we tied the sine and cosine curve to a position in a grid. Change in cell size will affect the pattern. It will affect the zoom. I think at this point we can already call it a flow field. I slowly increase zoom to show you how that value affects the pattern. I can go really into the pattern, zoom in close, and slowly I zoom out of it. Still, I don't think it's obvious what the pattern is. Let's go up here to particle class constructor. I can remove these initial values of speed x and speed y because they get immediately overwritten here inside the update method. I want each line to move at a different speed, so I will give each particle a speed modifier property, and it will be a random integer between 1 and 3. Down here, I multiply speed x and speed y by that speed modifier. Now, some lines move slower, some faster. Let's increase the speed modifier range. To show you clearly how curve and zoom affect the pattern, we need lines to reset when they finish their animation sequence. I create a method I call, for example, reset. When they reset, I set x and y coordinates to a new random position somewhere around the canvas. And I also need to set history array to these new values as the initial position with an index of 0. Right now, the line just moves endlessly somewhere far away off screen. I will create a property I call, for example, timer. It will be max length of the line times 2. For every tick of animation, I will decrease timer by 1. Timer starts as a value equal to max length times 2. It decreases by 1 for every animation frame. As long as timer is more or equal to 1, we will animate the line and make it crawl around like it does already. When timer reaches 1, the lines will freeze in place like this. At this point, we want an else statement to run, which will start removing old segments from each line one by one, making the line disappear from the end. I do that by calling shift on the history array. This will give us an error when we remove everything from the history array, but we still try to draw it, so I will only run this else statement if history array contains more than one element. Only then remove old segments from the line. So lines flow around. When the timer reaches 0, we start removing old segments until there are no more segments left. Perfect. At that point, I want the line to reset and repeat this animation cycle again, so else, call this .reset method we just defined on line 56. Okay, it's not working because I also need to reset timer back to its original value. Congratulations, you built a flow field. This is a very solid code base and we can do so many things with it. It's finally time to properly use curve and zoom to show you the pattern I was talking about. As we said, Berlin noise will create a natural looking gradient noise pattern. We are calculating angle values for our flow field on line 85 using trigonometry. So even though it doesn't look like it now, this is a very symmetrical mathematical pattern that repeats endlessly in every direction. Let me show you what I mean. Look what happens when I increase the value of curve. I really enjoy watching this effect. There is something very relaxing about this. I think now you can see a little bit that we have a repeating pattern. I change zoom and I zoom away from it to clearly see the repetition. I can also zoom really close into the pattern and we just look at the small part of it. Kinda looks like the flow is actually random, but we know it's not. I will increase the number of particles. My computer can handle this, but you should adjust the number of particles to make sure your computer can animate this smoothly, so you don't have to use 2000 particles here. Try different values and see. I don't recommend going much over 2000 unless you have a very powerful computer. Flow fields are such a beautiful effect, and now you know how to build one yourself. We are just playing with sine and cosine pattern here, but we can use this code to change the flow and make it follow many different patterns. Look what happens when I change the curve value. As the value gets higher, a spiral pattern will start emerging. Let me go a bit higher. It will start curving in a spiral here, and as I increase the value, it spirals more and more. It will kind of create a spiral snail shape if we go high enough. Now it's becoming more obvious. And even more, the curve just spirals in on itself. Interesting, isn't it? So now I think it's very obvious how the curve affects the spiral shape of the flow field. This pattern is endlessly repeating in every direction, and we can zoom in and out of it by changing the values we use as this.zoom on line 75. I can zoom really close into the pattern, and as I increase this value, we are slowly zooming out. At this point, we can see the repeating nature of this pattern as we zoomed far enough. I go even further. I can make it spiral more. Do you see how the pattern is jagged and not very smooth? This is exposing the grid-like nature of the flow field, as the angle only changes every 20 pixels. I can reduce the cell size to make the flow more smooth. I'm basically slicing canvas into smaller pieces, 5 × 5 pixels. As we can fit more columns now into the available canvas area, changing cell size also zoomed really far away from the pattern, and now you can clearly see how it's endlessly repeating. It's not random like Perlin noise, it's very mathematical and symmetrical. I zoom in, a bit further. I think it's clear how this works now. Feel free to play with it and do your own experiments. Flow field is basically a grid of angles. Let's visualize that grid to make it clear how exactly it works. Let's create a debug mode. On the main effect class, I create a method I call, for example, drawGrid. It will expect context as an argument. Inside, I create a for loop. First, let's draw vertical lines, columns. This .calls property already holds a value representing the number of columns in the grid, so we use it here. Every time we enter a new column, we call beginPath. I want to draw a vertical line. Move to method to define the starting x and y coordinates of the line. Each line will start at dynamic horizontal position. Cell size, the width of a single cell, times the number of the column we are currently in. All vertical lines will start at the top from y coordinate 0. Line 2 will determine the ending x and y coordinates of our grid lines. Horizontal position will again be cell size times column number, and I want the lines to end all the way at the bottom of the canvas area, so this.height. Then we stroke the lines. Let's see what we have so far by calling drawGrid method from inside render method. Nice! We see vertical lines representing columns in our flow field. Cell size is only 5, so we see line every 5 pixels. I change it to a 30. As you can see, this also affected the zoom into the pattern. As the cell size increased, we can fit less cells per row, meaning that the spirals created by sine and cosine on line 85 have less time to develop. It's all because we tied angle value we pass to sine and cosine to column and row numbers. Less columns, lower range of values passed as angle to sine and cosine on line 85, which affects the pattern. I can always make up for that by adjusting this.zoom property on line 75. Okay, we are drawing vertical lines. Let's also draw horizontal lines, the rows, to complete our grid. Again, we start by begin path. Starting x and y coordinates of each horizontal line will be 0 horizontally, so from the left edge of canvas, and vertically it will be cell size times the row number. Endpoint of each line will be the right edge of canvas, so this dot width horizontally. Vertical endpoint will be again cell size times row number. I stroke the lines. Perfect, now we can see the full grid. Look closely at the lines. Do you see how the angle value, the direction of the line, changes at the points as lines enter new cells in the grid? Each cell in the flow field has different angle value assigned to it, and lines follow those angles to give them direction of movement. This visual should help you understand how flow fields really work. And if you are coding along, you can inspect it from up close on your computer and really see what's happening. Change the value of cell size to even larger number, and the mystery of making flow fields should be solved. I want to make the lines of the grid thinner, but I don't want this change to affect the line width of the flowing lines. For that reason, I will wrap this entire code block between save and restore. These two built-in canvas methods make sure that any changes we make to canvas state will stay limited to a specific area. Those changes can include any canvas settings such as fill style, stroke style, line width, opacity, global alpha, as well as things like rotation and scaling, which we are not using today. If you want to know how to use rotate and scale, you can check out my class on fractals. If I set stroke style to red, it will only affect the grid, not the flowing lines, not the particle system. Save method creates a save point, like in a video game. We can make any changes we want in here. For example, line width only 0.3 pixels. These changes will affect this drawing code, and then restore will reset all the changes made back here to the point it was when we called save. Because of that, when we later draw the flowing lines, the particle system, using draw method on the particle class, they will not be affected by this stroke style and this line width at all. I want to keep the grid in our project, but I want a way for the user to be able to hide it and show it easily. I create a debug mode. Property called this.debug will be set to true initially. Same as we did with calling init here. When effect class gets instantiated, all the code inside the constructor will run. I can actually put any code I want in here, even an event listener. When we create an instance of effect class using the new keyword, at that point I want an event listener for keydown event to be applied. I need to make sure I still have access to properties on class constructor, specifically this.debug property from inside this event listener. If you use a regular callback function, you will have to bind it. Alternatively, I can use ES6arrow function. These functions automatically inherit this keyword from their parent scope, so even when this event listener runs later, it will still be able to remember it was originally defined here, and it will be able to control this.debug property for us. If you use regular callback function here, you will get an error because this keyword will become undefined. When keydown event happens, we console log this auto-generated event object. I decided to call it by a variable name e, but you can call it whatever you want. If I open this event object, down here, I can see it contains key property, which tells us what key was pressed. That's exactly what I need. If e.key is triple equals comparison operator to d, set this.debug value to its opposite. If it's currently false, set it to true. If it's currently true, set it to false. This is a very useful line of code that allows us to toggle between true and false easily. I only want this code to run if debug mode is true. I only want to see this flow field grid when debug mode is active. Now, if you click on canvas and press letter D on your keyboard over and over, you are enabling and disabling debug mode. We will use this debug mode again in the advanced class, where I show you how to trace letter shapes and images. Now that the individual cells in the flow field are relatively large, we can clearly see that the lines break and change direction at the boundaries of each cell, because each cell contains a different angle value influencing the motion of these lines. Feel free to play with the code, give different value to cell size on line 70, and then you can adjust for that change by tweaking this.zoom on line 75. You can come up with some interesting combinations, like here where I have a pretty interesting pattern that is clearly affected by the fact that individual cells in the flow field are 50 times 50 pixels. I will gradually increase the curve, the inner spiral of our sine-cosine flow field. Beauty of math. Did you know that you could make art with math like this? I open another browser window and I will Google Color Picker. I'm looking for something like this where I can click anywhere I want and it will give me that color value. You can go into any color range you want. I take this color by copying its hex value. I assign it as this.color property on particle class. Inside the draw method on particle class, I set stroke style to this.color. If the entire flow field was just a single color like this, there is no point calling stroke style over and over. I would declare it somewhere so it only runs once on the first page load to improve performance. But here I'm trying to give our particles a randomized color range. I create an array I call this.colors. I put this value inside like this. I go back to my color picker. I started from a dark color, so I go a bit lighter in this direction, for example. And again, I copy this hex value. I put that similar but lighter color in the array as well. This.color will be a color picked randomly from this.colors array. I can access them through their indexes. This.color index 0 is this one. This.color index 1 is this one. Let's take another color and add it into the array. I choose one more color, going even lighter. I choose one more. This time it will be very light. You can choose as many colors as you want. It doesn't matter how many colors you add into this array. I want each particle to be randomly assigned one index from this array. How do I do that? Of course, by using math.random between 0 and the length of this.colors array. However, math.random gives us floating point values. There is no index 1.5 in this array, so I need integers. I wrap all of this in math.floor. And this is how you can randomly assign one value from an array of available values to each object created by a class. You can see that each line has a random value assigned and our effect looks more interesting. Feel free to go back to the color picker and choose your own color range. It would probably be interesting to create sliders for this.zoom so that users can easily control it. You can do that as a challenge in the end if you want. If I resize browser window, as with every Canvas project, Canvas element will not resize automatically. In the same way, we are applying event listener for keydown event here inside effect class constructor. I can also create resize window event listener. We are inside a class, so I don't want to be pulling width and height from the outside. So let's console log this auto-generated event object. I remove this console log. And I also remove this one. So we are console logging event object that was auto-generated when we resized browser window and we triggered resize event listener. Inside I can see target of the event, in this case browser window object, and inside of that we can see the new updated inner height and inner width. So we will just use these values. I console log e.target.innerWidth and e.target.innerHeight. Now I can resize the browser window and I can see the new width and height. Perfect. So when we resize, I want to set width and height of the effect to these values. The problem is that we also need to resize canvas element itself, and I would again have to reach outside my class to grab it. I want to keep my classes modular. I need a reference to the canvas element inside my class. I refactor this code. Effect will expect only canvas as an argument. Inside, we convert it to a class property, and from this.canvas now we can take width and height like this. Line 69 now gives us access to the canvas element itself. I close the console. I need to take this canvas variable from line 1 and I need to pass it to effect class constructor at the point when we create an instance of effect class using the new keyword. Here on line 135. Inside, it gets converted to this.canvas property, and from there, width and height is extracted. So now, when resize event fires, I will call this.resize method, which we will write next, and I pass it the new width and height of the resized browser window. We get these values from this auto-generated event object. I will write this method down here, inside the effect class. We know it expects the new resized width and height as arguments. We have a reference to the actual canvas element here on line 69, so I take it, and I also take width and height. I copy these 3 lines and I paste them down here. When we resize browser window, we get new width and height. We set width of canvas element to the new width. We set height of canvas element to the new height. Then we set width and height properties of the effect to these new updated values. If I resize the browser window, it looks interesting, but I'm not sure if we are not wasting memory like this. If I go back to a smaller size, lines should eventually move back to the smaller available area, and then when they get more space, the pattern should expand to the larger space again, I think. The way I prefer to do this is to call init method again after the window was resized. Don't do what I'm doing now, don't run this code, because if I call this.init from resize method and I resize browser window, something very bad happens. We are pushing more and more particles into this.particles array and the effect slows down considerably. If I go up to init method, you can see that every time init method runs, we delete the flow field array and we refill it with new grid of angles. I need to do the same with particles. We set this.particles to an empty array, deleting all particle objects inside, and we create a new set of particles. Performance-wise, this is not the best solution. We don't need new particles. I could have just created a reset method on each particle, and I could have reset particle positions here, rather than deleting all of them and creating new ones to replace them. We could also use object pooling technique here if we need to increase and decrease the number of particles depending on canvas size. What I'm doing now works because I'm calling this.init method from inside resize on line 126. When we resize, we delete old flow field grid and replace it with a new set of angles, now adjusted to the new canvas width and height. And we also delete all particles and we create a new set with random positions spread over the new available canvas area. Of course, for this to work, we need to make sure we call this.init from resize method here. I assume most users will not be resizing the page over and over, so this solution is perfectly fine. The shape of the flow field is what I call sine and cosine spiral curve pattern, a bit of a tongue twister for people with my language background. I'm not sure if this shape has an official name. If it does, let me know please. It's the pattern you get when you use increasing positions in a 2-dimensional grid as angle values passed to sine and cosine. We see the formula here. This line of code determines the shape of the pattern. We can play with it in many different ways and get very different results. Look what happens if I replace multiplication with addition here. Or what about if I do that here? Or I try this. I adjust zoom. Interesting. I can also adjust curve. You can just randomly change the operators here and maybe you will stumble on something interesting that I haven't tried. Again, this is how I can slowly zoom out of the pattern. I can increase curve, and because of the changes to operator we made when calculating angle grid, it now changes the direction of the entire pattern. This looks nice. I could maybe use this effect for space background in the upcoming game development class. I could even make this react to some objects. We will learn more about that in the next part, where I show you how to make the lines flow around text. Surprisingly, doing less equals here will also change the pattern. It will become more apparent when I zoom out. I think this is because we change at which point the cells in the grid break to a new row. If I go back to multiplication, here we are back to the usual spiral pattern. I'm just playing with it now. I try changing zoom. I change curve. I can also do both sine here, or I can swap sine and cosine. I think it's clear how this works now. Feel free to play with it and do your own experiments. Join me in the next part to take this to the next level, or check the extended class where we learn how to make particles flow around images. We will also learn how to preserve the colors of the original image, which was a bit tricky for me. Took me a while to work out how to do it. Links in the description down below. Click the like if you found some value today. See you soon!